All right, so hopefully this has got the little quirks worked out of it. And it'll let me write today, but I guess we'll kind of see where we're at. All right. So we've talked about how. Okay, maybe it won't let me do anything today. It's gonna be a brat. There we go. We've talked about how we have a slow step of the reaction. You guys saw that on Thursday last week when you guys were trying to do your lab activity, the motion activity with the ping pong ball. The slow step then is going to determine your rate, and that's where your rate constant can be obtained from that. If your subsequent reaction, though, is slow, then you have to go in and you have to substitute where that came from. So, for example, down here, please let me write on this. No, I'm going to. There, now it's, no.
Happy Monday.
Happy Monday. So if B here if B is created in this first step and your second step is your slow step, you have to put where B came from, and then that becomes part of your rate law. Okay, so B came from 2A's up here. So B came from 2A's, so that becomes part of your rate law, and the 2A's go down here, and then your C goes in there as well. Okay, makes sense? All right. Now, so in cases where that slow step isn't the first step, again, we have to write that in, and we can also have what's called equilibrium, okay, where you end up having A and A on one side and B on the other, and A is forming from B and B is forming from A. And so at equilibrium, that is your fast step. And we'll get more into equilibrium when we get into Unit 7. Okay. So we can combine all of these values into a single rate constant, which is down at the bottom there. It's going to be almost impossible to do without being able to write. I just need stuff to work, you guys. Like, honestly, just need stuff. All right, well, let me write on here. Yes. Okay. All right. We have.
Yeah, I'm pretty sure my concealer is probably wrong. Because everything is just coated in concealer.
Okay, here we go. So they've given us the rate law here. Okay. This is the overall equation, but it's actually occurring in two different steps here. Okay. And they want to know which rate law, which step that rate law would apply to. Okay. So if it was this step, the rate law would just be 03. Okay. So it doesn't make sense that that's our slow step. Does that make sense? Jiving. Huh? That's not jiving. It's Monday and you can't come today.
I can't do anything.
All right. So if
why is it over oxygen? Why is the rate K032 over O2?
Because this is at equilibrium.
Oh, okay.
So because of that, we end up with that O2 in there. So oops. This is going to equal K1 -1. It's the reverse. Because this is at equilibrium. This is where I'm getting this equal from, is because this is at equilibrium. That's a double arrow. Okay. So equilibrium means that this is forming at the same rate that this is forming. And this is forming at the same rate that this is forming. Okay.
Okay, that makes sense.
All right. Now, O here, we need to isolate that because we need to figure out what it's equal to so we can substitute it out of here, because O is an intermediate. So we need to get rid of it in, we need to get that equal to so we can substitute that out in this part of the equation. Okay. So O, just using my algebra here, is going to equal K1 O3 over K minus 1 O2. I just isolated this and got it by itself. That's what I did algebraically. I divided both sides by these two items to get this guy by himself. All right. So now I'm going to go and write my rate law. We know that the rate law is this step. It's the slow step, because that rate law, had it been the first step, would have only had this in it, and it didn't. that wasn't just the first, that wasn't the rate law. So it can't be the first step. It has to be the second. Does that make sense? They gave us this. We know this. Had this rate been equal to this item, then the first step would have been your slow step. But it wasn't. This is your rate law. So it has to be the second step. Is that making sense? All right. So your rate law then is going to equal let me get rid of those. How did I get that to substitute out? Rate law is going to equal K. And then we're going to have our O3 here and our O3 here. So we've got to get this O3 in. Okay. And we're going to have two of those because we got another one from this guy. So I'm going to square that over this O2. And that's how they got this up here. Yep.
The O2, like did the K's cancel?
Yeah.
So the negative 1K canceled out.
Mm-hmm.
So where'd the other K come from?
The right here.
Oh, okay, square. Okay, and then so are we writing it for the second?
Yep. You're writing the rate law for the second because that's your slow step. All right. We do is next, which, come on. Oh, come on. Just work. Am I completely frozen up now?
No. This is what
I have black accents or black. That's fine. And my hair's not white though, so my hair also not white.
Remember one thing, a true friend would
Imagine if my hair was
said
just
anything
white.
before that.
Did you go to Spain? I recorded it. I was at Kansas. No, I heard it was. There was a blowout. Yeah.
All right, let's try this again. So this is our slow step here. All right. B and D actually came from up here. So our rate law for this is going to be rate equals K, which is your rate constant, times A, and that's going to be squared because we had a coefficient of 2 here. So you have to go back and find where these intermediates came from in order to substitute them in to become your rate law. Does that make sense? Maddie?
Would the K's cancel? Like, cause it's K1 and then K the -1.
Well, that was for this guy up here. So this is going to have this is going to have a K as well, which is what this one is.
Wait, it's K squared.
K sub 2. It's just saying it's a second step. It's not squared. It's not a superscript. It's just kind of identifying which step it came from. All right, moving on. Moving on up. So, multi-step reactions when we're looking at our graphing here. Okay, so we looked at graphs before where we saw different steps. Okay, so for example, we identified this as, is this exothermic or endothermic? Exothermic. And at the time when I showed you this originally, I only showed you this with one hump in it. Do you remember that? Well, now we've got the 2-humped camel. Sometimes we even have a 3-humped camel. Okay, so here's your 2 humps. The hump that is the highest hump, okay, that is your rate determining step. So find the hump with the highest profile here, and that's going to be your rate determining step. So these are right here, these valleys, these are your intermediates. All right, the first step though here, see how it ends up higher than this? The first step is actually endothermic. Okay, the second step then is exothermic, and the overall reaction is exothermic. Your activation energy that you need comes from, for the first hump here, comes from the beginning energy minus the top of that. That becomes your first activation energy. And then your next activation energy goes from the intermediate to the top of that hump.
So if the second hump was taller than the first hump, but the activation energy was less than the first hump, which one would be
the rate determining step is always the highest hump.
No matter what?
Yep. So I think this is what you're asking about. If we had something like this. If we had a situation like that, is that right?
But like only if like the first step still had a higher activation energy.
Okay. Like that?
Yeah.
Because this activation energy would be this tall. This activation energy would only be that tall. Yeah, I'm 99% sure that the first step is the highest amount here.
Okay.
The first or the second?
All right, second one. I'm sorry. Highest oh, no, it says the highest activation. I'm going to take that back. It says the highest activation energy corresponds to the slower step. So that is the key. I am going to backtrack on that, Derek, and I'm going to say that you are right. The highest, it's not necessarily the highest peak, it's the highest activation energy.
Thank you.
Yep. No, that's good. You guys keep asking questions. We'll get there. This is all a journey for all of us. Maddie?
They have one word. So the slowest step has the highest.
The slowest step has the highest activation energy. I don't think it's going to happen. Not in AP Chem, at least. That's a future problem you're going to have. All right. So this guy here, we have a reaction. This is our slow step. And you can see here that your activation energy is this much. So that is your activation energy for step 1. This is your activation energy for step 2. So that holds with our theory that our first step here is the slow step, and that has the greatest activation energy. Okay. Overall, this is exothermic because your products finish at a lower energy than your reactants. All right. So they just want us to have a 3-step mechanism where the overall reaction is exothermic. Everybody's graph could look slightly different than everybody else's graph for this. Which step do you want to make your slow step? First one, okay. All right, this thing isn't working at all now. All right, let's try it again. See if it'll work now. All right, you want your first step to be the slow step, yes? So I'm going to make that one a high pump. Okay, so here's my first step. We have EA here. EA1 we'll call it. This will be your activation energy 2. And this will be your activation energy 3. Okay, this is your slow step. It has the highest amount of activation energy. This is your next step and your third step. And overall, it's exothermic because your products are ending up with less energy than your reactants. And hopefully you were able to draw a little bit nicer and neater than I am, but we get what we can get done. Hey, oh, perfect. And can you cut those quizzes, not my original, but the quizzes into 3 piles? See the quizzes, they're
through like
One's-
the bottom?
No,
of the
didn't,
capsule?
right there. Yep.
These ones? Oh, these are clues.
Yeah, but don't do my top copy. Don't do my original. Yeah, cut those into thirds. See how they repeat?
Oh, cut 'em.
Yep. Thank you. All right.
Ew.
So here we've got energy profile. Our reactants are starting at 20. We have a transition state here at 80. And it doesn't matter on the x-axis where these are, as long as you're, the next one's further to the right of the previous one. Intermediate is at 50. And I usually draw my dots in, and then I go back and connect everything. And then down here at 5. All right. So now I'm going to try anyway. All right. That's as good as Lippy's going to be able to get it this morning, y'all. All right. So here's my first activation energy. Here is my second activation energy. Which one is my slow step? My first or my second?
All the way down to the 20. Your first step.
Because it's a Monday and I know not what I do. All right, let's try that again. Okay, better?
Yeah.
We will get it at some point. And then this is the change in energy for the overall reaction. That's our delta H, which we call enthalpy. And we'll get into that more in Unit 6. All right, so based on my revised drawing here, thank you. What is my slow step? Yep, this is my slow step. Step 1 is my slow step. And this is my faster step. This is my change in energy for the overall reaction. All right, makes sense? I'm ready to go with this one. All right, last section, catalyst. So what a catalyst does is it's going to be something that is not used up in the reaction. You could use it over and over and over again. And we have different kinds of catalysts. We have homogeneous catalysts and heterogeneous. Homogeneous are in the same phase, and heterogeneous then would be in 2 different phases. It's going to be different than the reactants. Okay. Now, what a catalyst can do, and often does, is it will take a reaction that would normally happen in one step with a very high activation energy. Sorry. It'll turn it into a 2-step reaction. Okay, so here we went without the catalyst. We had a 1 step, and that 1 step had a very high activation energy. Once the catalyst was introduced, it's going to take it in 2 steps, but those 2 steps aren't going to have as high of an activation energy. So you're able to perform a reaction with less energy input. Does that make sense? And then the catalyst is regenerated at the end, and it's able to be used again. And I kind of, when I talked to you about catalysts at the beginning of this unit, I said they're kind of like a car in a way, in that once you use it, you can still reuse it. Like it's not done. Okay. One of the other ones is that it will bind with one of the reactants, and that will change the orientation. So it makes it easier to do that kind of transfer and of energy. Okay, so here's an example of that. It goes in, it binds with it, it gives you a better orientation, and then it pops back out. Okay. All right, let's look at and try to identify some stuff here. What is this IO called? It appears here and here. That is your intermediate, yes. Okay. I don't have any other intermediates. I just have that one. Okay. Now, if we look at our catalyst, a catalyst will appear in the first step, and it appears the same at the very end. So that is our catalyst, right? It appears in the first step, and it appears in the very last step again, because it's coming back out, and now it can get reused. When we write the overall reaction, we get rid of the intermediates, and we get rid of the catalysts, and then we write what remains. Okay, so my overall reaction is H2O2, and I have two of those. I have one from here and one from here. Then I'm going to have on this side, I'm going to have two H2Os for these two right here, plus O2. And then this thing should balance. Okay, so I have 4 hydrogens and 4 oxygens. Over here I have 4 hydrogens, and I've got 2 plus 2 is 4 oxygens. So when you're done, make sure that your overall reaction balances. As a side note, intermediates do not appear in rate laws, but catalysts do. All right. So we want to identify our catalysts and our intermediates. So first of all, let's try to find our catalyst here. So I've got a catalyst in NO. So that is my catalyst. And then I've got one intermediate. I have this guy as an intermediate. So I'm going to get rid of my catalysts. I'm going to get rid of my intermediates, and then I'm going to rewrite this equation. So I have O3 plus O yields 2O2. And I balance. And that, my dears, is Unit 5.